Good morning, Doctor. This is Nachamba de Mariam from SWML 53. I'm sorry for the noise, but I'm going to explain an explainable dual module ensemble architecture for microcredit scoring under severe class imbalance and for institutional domain shifts. And these are the keywords. We have credit risk, gradient boosting, the loan default prediction, machine learning, Microsoft Circles in Uganda, microfinance. I'll go straight into the contents. The contents for our these are contents for our presentation. Basically, the background and introduction covers Uganda's Tier 4 finance sector. Uganda basically has over 20,000 savings and credit cooperatives and microfinance institutions, and it's managing 3 trillion Ugandan shillings annually outside the formal credit bureaus. And we assessed a portfolio at risk of 15 to 25% in Uganda, which versus the 5% globally. And that means that up to 25 Ugandan shillings per 100, which is lent, may never return. We looked at the basic reasons as to why this happens is that there is a credit bureau gap. Basically, since Uganda has Tier 4 institutions and they cannot check cross-institutional borrowing, and that means there is a silent double-dipping gap, which is undetectable. Then the appraisal bias, when people access loans and they're not credit-worthy, or someone accesses accesses a loan because of relationships being to like if you're known. And then our project basically uses two modules: the loan application gatekeeper, which works as a predisbursement default binary default predictor, and this one scores the application before money is disbursed. And then the second one, which is the loan monitor, it works on the post disbursement of the loans, and it works with a 3-class early warning, which has the stable, elevated, and critical for the active loan. So basically, this uses the details that are applied after at origination. Then we had the XG Boost. XG Boost used the gradient boosted trees, and it optimized the inductive bias for heterogeneous tabular credit data, which had missing names. And then we also had the SHARP, and this SHARP follows a model agnostic attribution, which satisfies Uganda's Data Protection Act in 2019. Then this is the area under precision curve, which had a metric of 3.1 to 1 class imbalance ratio. And then we also had a group shuffle split, which showed that SACCO had train and test splits, and models evaluated entirely on unseen cooperatives. This is the related work we had. I'll go through some. We had AI in banking, and the models we used for this is that it used the logistic regression, and then it also gave us a result of 0.1 area under curve. And the architectural limitation we saw is that since it is linear, it follows the nonlinear circle interactions, and the context limitation is that it requires formal credit history, which is not applicable to the Uganda's Tier 4 institutions. And then I also talk about the predicting credit risk in European P2P. Here, we have the neural net or XG. We use the neural net and XG Boost as the models, and then it was unstable on circle sets, and then the context limitation was that since it's a European P2P, repayment dynamics may differ from the circles in Uganda. I'll also talk about this, which is our module, an explainable dual module ensemble architecture for microfinance credit scoring under severe class imbalance and institutional domain shift. And it used the XG Boost, random forest, logistic regression, the tab nets, and the tab transformer, etc. And it had a single split in area under precision recall curve, and then it had the stability mean and on the seeds. Sorry about this. Then the architectural limitation is that there was the distributional shift across circles, and then the context limitation that for a single country there was federated learning, which is not yet implemented in Uganda. Appraisal, the problem statement, we included the appraisal bias, where I talked about that loan officers can approve loans based on relationships whereby someone can access a higher loan not because of the ability to repay, but because they are known by the loan officer, and that yields to losses because someone can access a loan that they cannot be able to pay at the end of the day. And then we also have the identity and trust gap. This majorly looks at borrowers who access loans without giving in their rightful details, or maybe use some other person's IDs, like how some people do in Uganda. And then there's a blind spot. The blind spot is where there are no early warnings for deteriorating loans, and by the time a loan is formally non-performing, the collateral may have been gone and recovery may be near impossible. The computational problem, we had class imbalance ratio, which was 3.1 to 1. And then we had the institutional leakage, the data quality crisis, and the minority class collapse. Because of time, I'll go straight to the dataset and dataset description and explanatory data analysis. And this dataset included 19,955 training eligible records, and these were from the circles across 15 districts, and it was filtered from the 20,855 raw records. Basically, the variables were these that we used. I'll talk about a few: the loan status, the borrower demographics, loan terms, application collateral, and it had a target of flagging of flagging one if it was a default flag. If it was a default flag. And then the privacy, we had all PIs were like the mobile money credentials, the NIN number, and the registration number. And these are some of the results. We had the class imbalance, the duration, default monotonic relationship, the borrower loyalty effect, and the school fit season of effect. This is explained in our IEE. I'll go to the model architecture and mathematical foundation. Our production model is basically the XG boost. This is the function for the XG boost. Basically, for the XG boost, it uses decision trees, and we had a couple of over 500 decision trees, yes, if I am to recall. So how it works, this works with it distills tree. It distills decision trees which are employed as a greedy, and then a depth limited recursive binary partitioning of the feature space, and then it minimizes the mean squared error on blended soft labels to produce a shallow and highly interpretable leaf probability rules that run in a constant inference time. The steps that it follows, I'll talk about this easier step. In tree 1, there is a rough cut where it predicts the residue from the base, and then sorry. And then when it goes to the second tree, it targets errors from the first tree, the errors that are left out in the first tree. Then when it goes to the third tree, it polishes out errors that were made, and it fixes that second tree's mistakes. And then we had like 600 trees, and then on the 600th tree, it has 600 tiny corrections in total. It also uses a sigmoid function, and this is the function that we used. I'll talk about the modules. I'll talk about a few because of time. We use the logistic regression, and for the logistic regression, basically it uses a linear leakage canary baseline, and here what it does, it computes it's okay. How I would say, it computes the data into linear format, and it uses a sigmoid curve. It has the weight, the bias, and it competes it in the X, and it produces the results. We will get the results soon. Then the random forest, it's a parallel committee of decision trees as well, and we had a total of 500 trees. This was the function that we used. Then the cat boost, this one works like categorizing. It categorizes and it's ordered boosting for circle heterogeneity. This was the function that we used. Then the light GBM, this one works with the leafwise growth for edge device efficiency. Basically, it looks at the best first leaf, and okay, it looks at the quality, the features that will have less effect. Oh, but it will but they will perform, they will give best results, and then it zeroes down to the ones that have a low rate. Yeah, that's how I can explain. Like, it starts from the ones that cause less effect, and goes to the ones that will cause high effect, to those that will cause low effect. Yes. And then we have the tabnet. This one uses a sparse mask to select relevant features per borrower, and the sparse mask, this is the sparse mask function. And then we also have the tab transformer. This one maps categories to dense bendings and contextually updates via attention layers. Here it uses attention layers, and this is the soft mask. It is applied on the soft layers of the of that data, and it performs as the function is applied, and it gives it's no, not that one. It's okay. And the output results are this. We can sample out logistic regression. This is the accuracy it had. It was 0.662. The F1 was 0.472. Then F2 was 0.603. The XG boost has 0.11, as you can see. Then I'll go to the next. This was the cross-cooperative stability analysis, and why we had to choose the production model being the XG boost. Basically, it being the first year, we had 6 splits in it, in XG boost. Random forest also had 6, logistic regression. Tabnet had 1, and tab transformer had 1. The rest also had 6, and basically, as you can see the results, we chose XG Boost because it had a stability mean test. In the F2, it was on 0.766, less than or equal, less or greater by 0.061, and it was running across 6 group shackle splits, and it reshuffled seeds from 100 to 105. It had a single fixed split test, which had an F2 of 0.61, and then it reflected a challenging partition of 30.14% test default rate. It had a shadow mode deployment, which was highly recommended. Tabnet and tab transformer are single seed, and they are not rank eligible for this model. Go to the next. This was the explainable AI results, and we looked at why some high-risk loans are highly rejected, and also why are some low-risk loans accepted. I'll go to the model. Yeah, the model. Basically, model compression works with knowledge distillation. Here we used 2. We had the primary level and then the teacher level. So the primary level looks at I would say the weak features. Then the teacher level looks at the XG boost model, like the complex features in the model. Then we had the extract, which is the first level. The extract reveals hidden relationships between classes by smoothing the teacher's confidence. Then the second transform, this is the transform function. It strips the sigmoid compression to retrieve the teacher's raw decision conviction. And then the distill creates the expert advice, which targets that the student model is trained to mimic. We had a distillation pipeline. Here in the distillation pipeline, we basically had a sequence of how can I explain? Like a sequence okay, a way of doing these things. We had the data loading and identical pre-processing. Here we're loading the data and the features that were to be used to identify what you are going to process with. Then we established a teacher's baseline. Basically, teacher's baseline just includes it's like a teacher's report card. Yeah, that's how I can explain a teacher's report card. Then we had to generate soft labels. Generating soft labels, here, the dataset is passed through the fitted teacher to extract probability distillations rather than the binary 0-1 inputs. We also had a loss blending. This is the feature that we use for the loss blending. We just train on the weighted targets, and then we also have the student training, evaluation, and selection. Here, basically, we trained three students, and then we see how they performed with each other. We had the student, then the distilled, and the let's see the results here. We had the teacher and the student baseline and the distilled students. These are the results that we had from them. And the XG boost is the teacher. You can see that the teacher had a threshold of 0.1, accuracy of 0.6, the F2, F1, and you can see that the decision tree, which is the distillation, had 0.1. Logistic regression, which is the distillation 2, is the other distillation. We also have 0.3. And then the gradient boosting module also had 0.2, and then logistic regression, which was the baseline, had 0.424327. Then the decision tree, which was the baseline, had 0.4, and the gradient boosting module had 0.1. We distilled again, and what we came up with was that the logistic regression had a negative 0.2, decision tree had 0.2, and GBM was small, which was 0.1. We basically considered the decision tree had 0.2. And the overall performance was that single decision tree student achieved significant performance over the 600 3x give boost teacher baseline. And this showed that the knowledge distillation was the regularization, that is, and the label smoothing effect was T to 2. Basically here, as you can see, the primary metric, which is the student, had 0.7412, and then the teacher had 0.61, and that is a performance retention. That student won the teacher. That's what I can say. In summary, our model selection based on XG Boost because it had a best cross-circle stability, as I explained in the earlier slides, and it confirmed clean causal effects. We also conducted a 7-step leakage audit, which passed the pre-disbursement plausible, and then we also had we also had to perform a deployment pipeline, which had the first one, and it included a shadow model, which the shadow model handles, okay, it runs parallel, it runs it runs parallel with a manual process, and it predicts the logged in, and then it shows no decisions are altered. Then the phase 2 has the assistant decisioning, which has high-risk applicants routed to senior officers with sharp list. And then we had the third phase, which is the policy integration. Because of time, this is the demonstration of the deploy of the default product. Sorry. This is how it looks like, our production model. After putting all the details, the product, the API generates a percentage, and it shows either the person has a high risk or has a low risk of defaulting the loan according to the details they have put. Then we also have the limitations. We first basically one was the data quality. We had 8 fully null columns, and we also had, so okay, Uganda's circle doesn't have a good high quality, that a good maintenance data quality. And then we had module 2 had an evaluation scope, and it failed because like GBM classifier deferred to a companion publication, and results presented majorly covered module 1. And then we also had a geographic institution focus, where the module performance may vary when applied to microfinance institutions in different geographic regions or economic jurisdictions, where lending behaviors and regulatory frameworks differ substantially. We also faced a class imbalance, and it was a 3.1 to 1 ratio. It means that there remains a challenge which potentially leads to a conservative scoring in volatile edge cases. In conclusion, we had a module which we used leakage audited machine learning credit framework on the Uganda's Tier 4 microfinance sector. We conducted a 24-question EDA. We conducted a 7-step leakage audit, and the future works we looked at getting all the target null fields, and then we also had to get a form of fairness edit. We also look forward to getting a federated learning. We get a cross-circle model improvement without raw data sharing or privacy preserving distributed protocol. We also looked at having the USSD model interface, where the USSD-based scoring interface for loan officers in areas with limited internet connectivity can access it. Then we also look forward to get that deep model stability, whereby the full tabnet and the tab transformer did not perform well because of the limited expansion. These are the references. And in acknowledgement, I acknowledge Dr. Galiwango Marvin and Dr. Efrens Yunis. And then Makerere University and the College of Computing and Information Sciences.